Hello everyone, and welcome to this presentation, Serial Protocol Fundamentals. This presentation is divided into 4 sections. The first is a general overview of serial protocols and their important characteristics. We'll then cover the 3 most common low-speed serial protocols, namely UART, I2C or I2C, and SPI or SPI. But before we start covering serial protocols, let's first spend a few moments discussing parallel data transmission. The earliest digital data transmission schemes were mostly parallel systems. That is, multiple bits were transferred simultaneously, with a separate conductor for each bit. In addition to these data lines or wires, many parallel data systems also had additional conductors for clock or control signals, such as handshaking. Parallel systems were also relatively easy to implement, with low cost and complexity, and they were commonly found in early PC architectures, for example, ATA, PCI, SCSI, etc. Early printer ports also used parallel data transfer. GPIB, the first standardized interface for remote control of test and measurement instruments, is also a parallel interface. However, parallel transmission is much less common these days, in part because of both speed and distance limitations, as well as because of the higher conductor or pin count required for parallel data transmission. Serial transmission, on the other hand, sends data 1 bit at a time over a bus, which may be shared with multiple nodes. In addition to a data line, other lines may also be present for things such as addressing, timing, control, etc. Serial transmission can be either synchronous or asynchronous. In a synchronous system, a separate clock signal is used to indicate when data bits are to be read. We'll look at examples of both types of systems later in this presentation. Serial data transmission has largely replaced parallel transmission in modern systems because it has numerous advantages. These include supporting longer distance connections, higher data throughput, and a higher node count. We also need to explain what we mean by a protocol. Generally speaking, a protocol describes 2 things: the meaning of bits and how they are formatted and arranged into messages, as well as the rules or procedures used when exchanging these bits or messages. A protocol also often defines other procedures that are necessary when sending data over a bus. For example, how nodes access a shared bus, how they handle errors, etc. For example, a node might start by announcing its intention to use the bus, and after being granted access, it would then send data in an agreed-upon format. If the data were not received correctly, the protocol might specify a procedure to follow for requesting retransmission of the data. Oscilloscopes are the primary tool used for analyzing and decoding serial and parallel protocols. Typically, each data line is connected to a separate scope channel, and special software within the oscilloscope is used to decode, parse, and analyze the messages. In many scenarios, an analog scope channel is connected to each conductor of the data bus. This has the advantage of being easy to implement and relatively inexpensive. It also allows the physical layer analysis of waveforms. This is particularly helpful when protocol failures are due to signal integrity issues or noise. Another way of connecting to a bus is using a digital or logic probe, which interprets inputs as digital signals. Logic probes are usually implemented as pods with 8 or more channels, so higher line or conductor counts are also possible. And in addition to decoding, most oscilloscopes also support advanced tools, such as triggering or filtering on certain message types or errored frames, exporting decoded messages, etc. Serial protocols are often grouped into families. The traditional low-speed serial protocols are UART, I2C, and SPI, and we'll be covering these in much more detail in the remainder of this presentation. Another common group of protocols are the so-called automotive protocols used in many vehicles. This group includes CAN and its variants, LIN, FlexRay, etc. A third category of serial protocols are those primarily used in aerospace and defense applications, such as Mil Standard 1553, ARINC 429, SpaceWire, etc. Higher speed general purpose protocols include the ubiquitous USB, as well as things such as PCIe. And finally, some protocols are grouped by the Defining Standards Organization. For example, MIPI standards such as RFFE for RF interfaces, or SPMI for system power management. So let's now take a deeper look at the first of the three low-speed serial decodes we'll cover in detail in this presentation, namely UART. UART stands for Universal Asynchronous Receiver Transmitter, and is one of the earliest serial protocols. The classic PC COM ports, RS-232 connections, modems, etc., frequently used UART for exchanging data. And UART is still in common use today, largely because it's very low cost, well understood, and very easy to implement. Unlike more modern serial protocols, UART can only connect a single pair of nodes. It does this by using two data wires that connect one node's transmit to the other node's receive. In this arrangement, the exchange of data can be simplex, that is in one direction only, half-duplex, or one direction at a time, or full-duplex, where both nodes transmit data simultaneously. UART transmits data in the form of frames, and we'll take a much closer look at these frames in just a few moments. But before we look at UART frames, we need to explain what we mean when we say that UART is asynchronous. Here, asynchronous means that the transmitter and receiver do not share a common clock signal. Although this greatly simplifies the protocol and eliminates the need for a separate clock line, it does place certain requirements on the transmitter and receiver. Since they don't share a clock, transmit and receive must run at the same speed, and since UART does not have a way to signal or configure this speed, the speed must be known and prearranged outside of the protocol. The most common UART baud rates in use today are 4800, 9600, 19.2K, 57.6K, and 115.2K. These numbers may look familiar to you, especially if you use modems or terminal connections. In addition to having the same baud rate, both sides of a UART connection also have to use the same frame structure. That is, each side must know how many bits are in each frame and the meaning of those bits. So now it's time to take a closer look at the bits that make up a UART frame. At a high level, UART frames consist of start and stop bits, data bits, and an optional parity bit. As with most digital systems, a high voltage level is used to indicate a logical 1, and a low voltage level is used to indicate a logical 0. But the UART protocol doesn't define specific voltages or voltage ranges for these levels. You'll sometimes also hear the high voltage level called mark and the low level voltage called space. One important thing to note is that in the idle state, that is when no data is being transmitted, the line is held high. One advantage of this is that it allows easy detection of a damaged line or transmitter. A UART transmitter needs some way to signal to the receiver that data bits are coming, and this is accomplished using the start bit. The start bit is essentially nothing more than a transition from the idle high state to the low state, and user data bits come immediately after this start bit. After the data bits are finished, the stop bit indicates the end of user data. Depending on the value of the final data bit, the stop bit is either a transition from low back to high, or idle state, or simply remaining at the high state for an additional bit time. A second optional stop bit can be configured, usually to give the receiver time to get ready for the next frame, but the use of a second stop bit is uncommon in practice. The data bits are the user data, or useful bits, and come immediately after the start bit. There can be 5 to 9 user data bits, although 7 or 8 bits is most common. These data bits are usually transmitted with the least significant bit first. Let's look at an example. If we want to send the capital letter S in 7-bit ASCII, this is the bit sequence 1010011. We first reverse the order of the bits to put them in least significant bit order, that is 1100101. We then send them out. After the last data bit is sent, the stop bit is used to end the frame, after which the line returns to the idle state. A UART frame can also contain an optional parity bit that can be used for error detection. This bit is inserted between the end of the data bits and the stop bit. The value of the parity bit depends on the type of parity being used. In even parity, this bit is set such that the total number of ones in the frame will be even. In odd parity, this bit is set such that the total number of ones will be odd. Let's look at an example. We'll use the ASCII value for capital S again, which contains a total of 3 zeros and 4 ones. If we're using even parity, then our parity bit is 0 because we already have an even number of ones. On the other hand, if we're using odd parity, then our parity bit has to be 1 in order to make the frame have an odd number of ones. It should be clear that the parity bit can only detect a single flipped bit. If more than one bit is flipped or errored, there's no way to reliably detect this using a single parity bit. Let's briefly summarize UART. UART stands for Universal Asynchronous Receiver Transmitter and is a simple two-wire protocol for exchanging serial data between a pair of devices. Asynchronous here means that there's no shared clock or timing between the two nodes. This in turn requires that the baud rate and frame length be pre-configured on each device. UART uses start and stop bits to frame the user data, which is usually 7 or 8 bits long, and an optional parity bit can be used to detect single-bit errors. Although UART is a relatively old protocol, it's still widely used for low-speed, low-throughput applications, although more modern protocols such as I2C and SPI are now commonly used for more demanding applications. Therefore, let's move on and look at these two newer serial protocols, beginning with I2C. The Inter-Integrated Circuit Protocol, commonly called either I2C or I2C, was developed in 1982 by Philips, now part of NXP. It's one of the most common serial protocols, and, as the name implies, it's primarily used for short-distance data communications. I2C is a synchronous master-slave type protocol, in which both the master and the slaves can send or receive data. It operates bidirectionally in half-duplex mode and can run at different clock speeds. Only two wires, serial clock and serial data, are used in I2C. We'll begin with a basic I2C topology. A master is connected to one or more slave nodes via two shared lines, SDA or serial data, and SCL or serial clock. These two lines are each connected to a voltage, VCC or VDD, by a single pull-up resistor. We'll explain the role of these resistors later in this section. Note that devices can be added to or removed from the bus at any location and at any time. Like UART, I2C nodes exchange data over this shared bus in the form of frames. Let's begin with a high-level overview. An I2C master claims the bus by means of a so-called start condition. Because I2C can support more than two nodes, the master then needs to send the address of the slave it wishes to communicate with, as well as an indication as to whether it wishes to read data from or write data to the slave. The slave acknowledges its presence and its readiness, after which the data is transmitted and acknowledged. The communication is terminated by means of a stop condition. Let's now go back through this frame and explain each of the fields in more detail. Similar to UART, in I2C, the idle state of both lines, SDA and SCL, is high. The start condition occurs when a node first pulls SDA low and then pulls SCL low. Pulling these lines down in this order is used to claim the bus, and the node that claims the bus is now the master. This procedure prevents other nodes from taking control of the bus, and thereby reduces the risk of contention, that is, two nodes trying to claim or use the bus at the same time. The risk of contention did not exist in UART because UART has only two nodes, and full-duplex communication between these nodes was possible. Once an I2C node has seized the bus, that node also begins sending the clock signal that's used by both the master and the slave. Again, this is unlike UART, which is asynchronous and does not have a separate clock line. Immediately following the start condition is the slave address, which is used to specify which node the master wants to communicate with. Each node on an I2C bus must have a unique, fixed address. These are normally 7 bits long, with the most significant bit first. I2C also supports 10-bit addresses, but these are uncommon. Addresses may be hard-coded for each device, but in many cases the address is partially configurable using external address lines or jumpers. For example, addresses for this board can be partially configured using 3 jumpers. In order to configure this address, both A2 and A0 would be jumpered, and A1 would be left open. At this point, it would be a good idea to pause for a moment to talk about the timing relationship between the data and clock lines in I2C. In this diagram, we can see that SDA does not change between the rising and the falling edges of the clock signal. Data is always read during the middle of the clock pulse. Expressed another way, we can say that during data transmission, SDA only transitions when the clock is low. This is necessary because an SDA transition when the clock is high would indicate a start or stop condition. Immediately following the slave address is the read-write bit. This bit is set by the master to indicate if it wants to perform a read or write operation. If it's set to 0, this means the master wants to write data to the slave, and if set to 1, it indicates the master wants to read data from the slave. Recall that the standard slave address in I2C is 7 bits long, and in many cases the read-write bit is decoded or interpreted as part of the address byte. The acknowledgement or ACK bit follows the read-write bit and is sent by the receiver each time a byte of data is received. A 0 is an acknowledgement, and a 1 is a negative acknowledgement, or a NAC. Recall that the I2C bus is idle high, so if the receiver doesn't actively respond by pulling the line low, this will be interpreted as a NAC. Every slave address or data byte is followed by an ACK bit. An ACK bit following a data byte is sent by the receiver to confirm correct reception of the data. An ACK following a slave address is sent by the address slave to indicate that it's both present on the bus and that it's ready to read or write data, depending on the state of the preceding read-write bit. The address ACK bit is followed by the data byte, which is actual information being transferred between the master and the slave. Although this is often the contents of a memory address or register in the slave device, this may be an address location itself. We'll talk more about this on the next slide. Data is always sent as 8-bit bytes in I2C, with the most significant bit first. Every transmitted byte is followed by an ACK bit, which, as mentioned on the previous slide, is set to 0 by the receiver when the data has been properly received. In many cases, multiple data bytes are sent within a single I2C frame. Additional bytes are simply concatenated onto the previous byte, although note that each data byte must be individually acknowledged. I2C doesn't specify the content or the purpose of the data bytes. These bytes may all be data, but often one of them will indicate an internal address or register location in the slave device. For example, if the master wants to write a certain value to a specific register within the slave, the first data byte might be the address or location of that register, and the second byte would be the actual data that's to be written to that location. In UART, the number of data bits, and thus the frame length, is fixed. but in SPI the number of data bits or bytes can vary. Therefore, there must be a way to indicate that the final data byte has been sent, and this is done using the stop condition. First, the SCL line is allowed to return high and remains high, and then SDA returns high and remains high. Recall that for data bytes, SDA only transitions when the clock is low. If SDA transitions when the clock is high, then this unambiguously indicates the stop condition. After the stop condition, the bus becomes idle. There's no clock signal, and any node on the bus can use the start condition to claim the bus and begin a new communication. Let's now come back to the role of the pull-up resistors in I2C. As we know, SDA and SCL are both normally high, and this is because each of these lines is connected to a voltage via a so-called pull-up resistor. Note that there's one resistor per line, not per device. Each I2C device contains logic that can open and close a drain. When the drain is closed, the line, SDA or SCL, is pulled low because it's now connected to ground. When logic causes the drain to be open, the line goes high because it's connected to voltage. Remember that in I2C, the idle state of the lines is high, and therefore you may sometimes hear I2C referred to as an open drain system. Pulling an I2C line down to ground is usually much faster than pulling that line back up to idle voltage. The time required to pull a line back up is a function of both the capacitance of the bus as well as the values of the pull-up resistors. The values used for the pull-up resistors represent a compromise. Higher resistances increase the time needed to pull up the line, and this in turn limits the maximum bus speed. Lower pull-up resistance values decrease pull-up time and allow faster communications, but this also requires higher power. Typical I2C pull-up resistor values are in the range of about 1 kiloohm to about 10 kiloohms. Pull-up resistance values are one of the factors that limit the maximum bus speed. I2C can operate at various bus speeds, often referred to as modes, and this table shows the maximum speeds achievable for each mode. Hardware is categorized as supporting one or more of these modes, meaning that the device can, theoretically, achieve the corresponding speed. But in many cases, bus speed is limited by other factors, such as the ones mentioned on the previous slide. The last two modes achieve higher speeds by modifying standard I2C behavior. High-speed mode devices are backwards compatible to the lower speed modes, but can temporarily switch the bus to high-speed mode by transmitting a special sequence. Ultra-fast mode is unidirectional, that is, it's write-only, and also makes modifications to the standard I2C protocol and frames. Let's sum up I2C. I2C is widely used for exchanging data over short distances using two wires, serial data and serial clock. In I2C, a master seizes control of a shared bus and then reads or writes data in the form of a frame containing the target slave address and one or more bytes of data. Each of these data bytes is individually acknowledged, and special start and stop sequences are used to mark the beginning and end of the frame. Pull-up resistors and an open drain are used to create the high I2C idle state. Devices can be categorized by their maximum supported speed, but the practical data rate on an I2C bus is also a function of the pull-up resistors and overall bus capacitance. Now let's discuss the last of the low-speed serial protocols that we'll look at in this presentation, SPI or SPI. SPI is a 4-wire serial interface. Recall that both UART and I2C only used 2 wires. SPI was originally developed by Motorola in the 1980s and provides speed improvements over the other serial data protocols we've looked at. SPI also has the advantage in that it can support full-duplex communication, which I2C cannot. However, SPI is somewhat loosely defined in that it does not specify frame formats, number of bits transmitted, or even voltage levels. SPI is most often used for transferring data between a smart controller and a less smart peripheral device. Many applications use SPI, some of the more common being different types of sensors, displays, ADCs and DACs, real-time clocks, wired game controllers, etc. Like I2C, SPI is also a master-slave protocol, with a single master and one or more slaves. The master is sometimes called the controller, and slaves are sometimes called peripherals. Master and slave are normally connected by 4 wires, although in some special cases, not all of these 4 wires are required. The chip select wire is used to select which slave the master wants to communicate with. The synchronous clock signal is used to provide timing and synchronization. Data from the master to the slave is sent on MOSI, that is, master out, slave in, and data from the slave to the master is sent on master in, slave out, or MISO. Let's start with a high-level overview of SPI. The master pulls the chip select line low to indicate to the slave that data is incoming, and then starts the clock. The MOSI line is used to send bits to the slave, and if the slave has bits to send to the master, these are sent using the MISO line. At the end of the communication, CS is pulled back to high. Next, we'll discuss each of these steps and lines in more detail, and explain both various configuration parameters, as well as how a master can communicate with multiple slaves. The first line we'll look at is CS, or chip select, which is also commonly referred to as slave select. Unlike most of the other signals in SPI, CS is typically active low, and therefore you'll often see it written with an overbar. As mentioned a few moments ago, communication with a target or slave is initiated by pulling the CS line low. The attached slave then listens for the clock and MOSI signals from the master. When communication is complete, CS is returned to its idle state. The greatest advantage of using chip select is that it's a very simple way to address targets. It doesn't require the kind of explicit addressing used in I2C. In the case of multiple slaves, these can be addressed using either a single CS line or multiple CS lines. After the master pulls CS low to initiate communications, it then begins to generate the clock signal. One of the advantages of this arrangement is that slaves do not require their own clocks, even when they're transmitting data to the master. SPI does not have standardized clock rates, but typical maximum speeds are in the megahertz range, which means that SPI is usually faster than UART or I2C. The purpose of the clock is to indicate to the receiver when the data should be sampled, that is, at what time the voltage level on the data line should be read. As with most other digital data transmission schemes, 1 bit is read per clock symbol. The clock signal in SPI can either be idle at a low state or at a high state, and data can be sampled on either the rising or falling edge of the clock signal. We'll cover this topic in much more detail in just a few moments. Once the CS line has been pulled low and the clock has been started, MOSI is used to send data from the master to one or more slaves. This data is usually sent in the form of 8-bit bytes, either with the least or most significant bit first. The number of bytes sent is also implementation dependent. SPI can send multiple bytes sequentially over MOSI, and the protocol also allows CS to be held low while sending multiple bytes. But, like many other things in SPI, this behavior is also implementation dependent. MISO is used to send data from the slave to the master. Note that not all SPI implementations use MISO. There are many kinds of devices, such as displays, that only receive data from a master, and this is an example of where SPI may use less than 4 wires. MISO data is also commonly sent as a response to data received on MOSI, for example, queries for data, commands to set parameters, etc. Remember that in SPI, only the master generates the clock signal, so in order for a node to transmit data on MOSI, the master must know how many bits the slave wants to send, so that the master can generate an appropriate number of clock cycles. This may be a fixed amount, or something that the master learns from querying the slave. Now that we've discussed the basics of SPI, there are three other aspects of SPI that we need to go over. The first two are clock polarity and clock phase. As we'll see, these must be configured identically for all connected SPI nodes. The third topic is an overview of how multiple slaves can be connected to a single master. As mentioned earlier, the serial clock signal generated by the master can be either active high, in which the idle or non-clock state of the line is low, or it can be active low, where the clock is held high when no clock pulses are being sent. C-pole is used to indicate which of these is being used. C-pole 0 means active high, and C-pole 1 means active low. For both types of clock polarity, we can refer to the leading or first edge of a clock pulse and the trailing or second edge of a clock pulse. Note that for C-pole 0, the leading edge is a rising edge, and for C-pole 1, the leading edge is a falling edge. Using the terminology leading or first edge and trailing or second edge can help to avoid potential confusion or ambiguity. This will be important for our next topic, clock phase. In SPI, a receiver may sample the MOSI or MISO data on either the leading or the trailing edge of a clock signal, and this is referred to as the clock phase. There are two possible clock phases. Clock phase 0 means that data is sampled on the leading edge or first edge of each clock pulse. Clock phase 1 means the data is sampled on the trailing or second edge of each clock pulse. In both of the examples here, the clock signal has polarity 0, that is, the clock is idle low. Two types of clock polarity and two types of clock phase yields four possible combinations. These parameters are often summarized as a single number, 0 through 3, which is called the SPI mode. As you might imagine, all interconnected SPI devices must use the same mode. Mode may be either fixed in hardware or user configurable depending on implementation. Note that the mode can often be determined by inspecting the SPI waveforms. For example, here we can see that the clock signal idles high, so clock polarity equals 1. We can also see that the data is being read on the trailing edge of each clock pulse, so clock phase also equals 1. Therefore, SPI mode 3 is being used in this communication. Note that of these four modes, mode 0 is, by far, the most common mode used in SPI implementations. The last topic we'll touch on is multi-slave configurations. One way a master can communicate with multiple slaves is by having a separate CS line for each slave. To address a slave, the master pulls that slave's CS line low. All other wires, that is clock, MOSI, and MISO, are all shared between the nodes. This configuration is often referred to as independent slaves. Although this method is relatively straightforward, there can be issues scaling it above more than a few slaves, due to the need to have a separate CS line for each slave. The other common multi-slave configuration is called cooperative slaves, or a daisy chain configuration. Here, the master has only a single CS line which is shared among all slaves. And, as with independent slaves, the clock signal is also shared among all slaves. However, in this configuration, MOSI data is sent to the first slave, and then additional clock cycles can be used to pass it along to the next slave in the chain. This is done by connecting the first slave's MISO to the second slave's MOSI. This process can be repeated to pass data to the next slave. If the first slave wanted to send data to the master via its MISO line, this data is routed in the same way, from slave to slave, until it reaches the last slave, whose MISO line is connected to the master's MISO. Although cooperative mode reduces the number of required CS lines, it is more complex and may not be supported by some SPI devices. Let's summarize what we've covered in this section. The Serial Peripheral Interface, abbreviated SPI or SPI, is a very common four-wire interface that's used to transfer information between a controller or master and one or more peripheral devices or slaves. These 4 wires are chip select, serial clock, master out slave in, or MOSI, and master in slave out, or MISO. The CS line is used for addressing, and MOSI and MISO are used to transfer data from and to the master. The SPI clock signal can be either idle low or idle high, and data can be sampled on either the leading or trailing edge of clock pulses. Note, however, that the clock polarity and clock phase must be the same for all nodes. These parameters are usually summarized in the form of a mode number. And finally, multiple slaves can be connected to a single master either independently, that is, with a separate CS line for each slave, or in a cooperative daisy chain arrangement. We'll end this presentation with a general summary. Serial transmission is the most common way in which digital data is moved from one device or component to another. There are many serial protocols, and in this presentation we cover the 3 most common low-speed serial protocols, namely UART, I2C, and SPI. Like all protocols, these define how data is exchanged. This includes message or frame format, as well as tasks such as managing access to the bus, acknowledging data, error handling, etc. Protocols may be asynchronous, such as UART, but as we saw with I2C and SPI, higher bus speeds generally require a shared clock line. Furthermore, if a bus contains more than 2 nodes, the protocol must also include a way to select or address them. Analyzing, decoding, and troubleshooting serial protocols is most often performed with an oscilloscope, using either standard probes or special digital or logic probes to acquire the individual lines. This concludes our presentation, Serial Protocol Fundamentals. Thanks for watching.